Hi everybody and welcome. Today we're going to be taking a look at synthetic division and its applications, specifically some of the challenge questions that might come up when we're looking at synthetic division problems. So and question that is a fair question might come up is, Mr. Eden, when are we going to be using synthetic division? What's something that it could apply to? So actually solar panels is one of the best examples of this because the angle of the sun and when it hits on the panels differentially. And an application of this is the Mars rovers that NASA was using ran on solar energy. So they would recharge their batteries from the sun, and that's how they would continue to work. But they didn't always know how much power was being applied to the robot based off of how much direct sunlight it was getting. And the angle of the sun changed the amount of charge that it got, and it wouldn't always be the same amount. So what they would see is the sun would hit the solar panel on it, and basically what they had was a calculation for the total area and one for the total width, but they weren't sure what the length was. So this is a real application of when they took area and divided it by width. That's something that they were able to get the solution for length with. And in this case, when we have area divided by width to get length, because it was changing based on the angle of the sun, it involved variables. So they actually ended up defining polynomials using synthetic division specifically to solve for that. So a cool application. We're going to come back to this actually in a moment after we work through some of our examples. As kind of the culmination of everything we're doing to see that we can actually solve for that length of the Mars rover area solar panel charging system. So jumping in for today, we're going to start off with a definition and then move from there. So we're going to take a look at degree of a polynomial. So this is just a refresh of something that we're familiar with, but we want to make sure that we're using the exact terminology accurately here. So degree of a polynomial, what this one does for us is it tells us the amount of variables in a given term. So in the case of synthetic division, when we see something like x to the second plus x to the third minus 4, we have to make sure that we are first putting them in order. So our first term is a second degree term. Our second term actually is a third degree term, and our last term has no variables. It is a 0 degree term. So by putting it in order, first we could see x squared plus, x cubed plus x squared second, and then our 0 degree constant goes third. But the second thing for synthetic division is no skipping. So what we'll see here is we start off with x to the third, which is a third degree, go to x to the second, which is a second degree, and we don't have a term for our first degree for just our x. So because we don't have that term, that's where we put in our 0. So we basically manufacture a term that doesn't exist by just labeling it 0, which doesn't affect anything because 0 times anything, just 0. But the idea here is we're keeping our order constant. We're going from a third degree to a second degree to a first degree to a 0 degree term. So once we have it in order and we're not skipping any degrees, that's what gets us prepared and ready to synthetically divide. So our first example, a good warm-up here. Start off second degree, first degree, 0 degree. So we're happy there. And we also know what our coefficients are here. So if there's nothing in front of it, remember it's just a 1 that's hiding there. So we have a 1, a minus 7, and a 10. The second step that we worked on yesterday in class was take whatever we're dividing by, and we're just going to set that equal to 0. So fully solve for this and get a concrete answer, which in this case is 1, and that's what goes in our box off to the left, is that answer of 1. So from here we follow our synthetic division steps. We drop our first term down. Anything below the line gets multiplied by what's in the box, which in this case is just 1. So 1 times 1 gets us 1. Anything above the line we combine. So don't think about it as addition or subtraction. We're just looking at putting things together. So minus 7 and positive 1 put together get us minus 6. As our final step here, again, anything below the line gets multiplied. So multiply negative 6 times 1, and we end up again with negative 6. Anything above we combine. So 10 and negative 6 combine to get 4. So this is an instance where degrees come back to us. So we always read this right to left. Remainder comes first, 0 degree term comes second, and then first degree, and so on. So we follow it at 0, 1, 2, 3, 4, as many terms as we have. So remainder always goes over what we divide by, which is highlighted in red. Our first term, the -6 with no degrees, is our first constant, so we just leave it as is. And our first degree term gets an x to the first power, because there's one x in that term. It's a first degree term. So we finish this up, we have our full answer, and there it is. So that's basically the steps that we're following for synthetic division. Now, what today's example is going to do is take us through some steps of what happens when we are presented with more challenging questions. So following our steps here, we want to do exactly what we did to start. Our first term has 2 degrees, and our second term has none. So it looks like we went from 2 to 0. So because of that, we have to correct this, add in our 0 term. And what this does is it brings us from 2 degrees to 1 degree to 0 degrees. So no longer skipping, so we're happy about that. The second thing that we do is we take our term that we divide by and set that equal to 0. So adding 8 to both sides gets us an answer of 8. So 8 goes on the outside, and then we bring down our coefficients here. So 1, 0, and -74. So following those same steps, drop our first term. It's below, so it gets multiplied. Combine 0 and 8 to get 8. It's below, so it gets multiplied. So 8 times 8 gets us 64. So we're left with -10. So once again, remainder, 0 degree, first degree. Remainder goes over what we divide by. Our h just stays as it is. And then we put an x on our first term. And that's our full answer. So synthetic, once we get into the steps, is quick. But the key thing that we did on this question, highlighting in yellow, is adding in that 0x term because we can't skip degrees. So that helps us with not skipping a degree. Moving on to our second example here. This one, it gets challenging because when we are solving for what we divide by, we have a couple more numbers here that makes this just a little bit more difficult. So as always, drop our constants down, so 2, -17, and -38. Just double checking these: second degree, first degree, 0 degree. So we're happy there. There aren't any skips. So we'll take our 2x plus 3 and set it equal to 0. Subtract 3 from both sides, and divide by 2 on both sides as well. So if you want to leave this as -3/2, or if you want to leave it as -1.5, either way works. Whatever is easier for you when you're working through. So put that into our box, and we can start our division steps. So drop our first term and multiply it. So when we multiply this here, I think we should get an answer of -3. And then we can combine our terms here, and that should get us -20. And then -20 times our 3/2 here should get us an answer of, and then we can multiply these out. So again, this is a good place to use a calculator for, especially when these numbers get just a touch bigger, but that should get us -30, or +30, sorry, because we get 2 negatives canceled to get us that positive number. So -20 times -1.5 gets us +30. And then lastly, -38 plus 30 together get us -8. So this -8 is our remainder. We have our constant, and we have our first degree x term. So -8 over 2x plus 3. Leave -20 as it is, and put our x next to our 2. And that'll be our fully divided answer there. So one final example that kind of puts both of these things together is when we have a second degree skips down to a 0 degree, and we have an instance here where we have a little bit more solving to do when we're taking a look at getting our term that we put inside of our box here. So first thing that we want to do is put in our first degree 0x term, so we're not skipping anything. And then second, we can take 7x plus 7 and set that equal to 0. Subtract 7 from both sides. Divide by 7. should get x equals -1. So now we can put -1 on the side, drop down 42, 0, and -33. Put our line below, and then drop 42 down. Multiply by -1. Drop that down as well. Multiply again by -1. And then we'll be left with our remainder term. So remainder, 0 degree, first degree. So 9 will go over 7x plus 7 in this case. And then we'll have x as our first term here. So these are kind of all the combinations of tricky ways that synthetic division can be presented to us. So in this case, we're ready for it. We have our steps down, and we know basically that we don't want to skip any terms. We know to add in a 0. We know when it gets complicated, we still just set it equal to 0, and whatever that final answer is, that's what we put into our box off to the side here. So those are the points of emphasis for today, just kind of anticipating any of the things that might be challenging to us as we work through these questions. So now that we've done this, take a moment and work through what is the length of the Mars rover dependent on x. So do this division problem. So just to check your work, we're at the end of the video now. 1, -1, and -2. In our box, we should have -3 after solving. So drop the 1 down. And that should be our full final answer for solving for that length of the Mars rover, which now we know how to do based off of our knowledge of synthetic division. So we can help NASA out. They can give us a call if they're not sure where to go. All right, as always, if you got questions, let us know. Thanks for watching.